Logistic regression is an OG data analysis technique that's useful to any professional. This crash course is designed for a broad audience, so there'll be a little bit of math. However, the focus of this crash course is on building your intuition of the how and why logistic regression works, rather than focusing on the minutia of the mathematics. Before I get started, if you'd like to follow along with the course, check out the description below the video. There's a link where I can send you a PDF of all the slides of this particular crash course, the Python code, and the data file. So if you want that, check out the description below. So let's go ahead and get started now and focus on this idea of why would you even want to learn logistic regression in the first place? To fully understand why you would want to go through the effort to learn logistic regression in the first place, we need to think about the landscape of analytics. And this is a common conceptual framework that I use, where the framework basically breaks down all the different types of analytics into a maturity model. So you can think of this as being the least mature, generally speaking, and this being the most mature. And what we want to do is go through this and then put logistic regression in the context of this maturity model, this framework, to understand what value it could potentially bring you as a professional. So first up, we need to talk about descriptive analytics. And this is basically the realm of traditional business intelligence, reporting, that sort of thing. And at a high level, what descriptive analytics is all about is describing what happened in the past, what happened last week, last month, last quarter, that sort of thing. So this is a very, very intensive part of most organizations' investments in data, to be quite honest, because it's foundational. You have to be able to tell your leaders what happened. Now, moving up on the maturity curve here is diagnostic analytics. And at a high level, that's all about why it happened. So descriptive is about the what, and this is about the why. For example, sales are down for product X last quarter. Why did that happen? That's the next level. Trying to explain what's going on in the business, trying to provide the explanations that lots of leaders want when they see something they don't like. So diagnostic analytics is the next level up. And essentially, you need more skills to do diagnostic analytics than you need to do descriptive analytics. And I'll talk more about that here in a second or two. And then next up, we have what's all the rage, predictive analytics. What is likely to happen in the future? So this is all about using your historical data and building predictive models to then project and say, what's likely to happen in the future? And by the way, generative AI, LLMs, large language models, all of that actually fit into this particular bucket because they are predictive models. They're very sophisticated, very large, very powerful predictive models, but they are predictive models in the end. Okay, so this is all the rage. This is data science, generative AI, so on and so forth. That's the next stage. And at the very highest stage, there's this thing known as prescriptive analytics, also known as operations research. And this has actually been around for quite a while, since like World War II. And prescriptive analytics, or OR, operations research, is all about how to optimize processes. So for example, prescriptive analytics really became a serious area of study during World War II because the Allies, the US and the Allies, needed to figure out how to optimally move men and equipment around the globe to various parts of the war. So this was a really serious endeavor. And since then, it's also been very, very powerfully used in things like industrial engineering, supply chain management, that sort of thing. So this is really at the top where it says, look, provide essentially the tool of description of what's going on in your business process. And it tells you exactly how to optimize it, how to allow workers to move quickly around the factory, how to minimize your shipping costs, that sort of thing. So those are the 4 levels of analytics. Now, what's really super important is this idea that true data analysis only starts at the level of diagnostic analytics. Description isn't analysis. That's actually a quote from one of my favorite authors, Dr. Donald J. Wheeler in the data space. Description is not analysis. So you need to be able to do at least diagnostic analytics and predictive analytics at a minimum to do true data analysis. And as it turns out, logistic regression is a predictive modeling technique that you also use often to analyze your data in a diagnostic fashion. You're trying to find the underlying levers, the underlying drivers of some outcome of interest based on your historical data. So oftentimes predictive models are often used for data analysis, and then they become more diagnostic analytics tools. So let's talk about logistic regression in particular. So logistic regression is a predictive modeling technique, like I said. And in this crash course, we're going to study a particular form of logistic regression known as binary logistic regression. Now, this is a form of logistic regression that's useful to any professional because basically what it does is it allows you to create a predictive model where the outcome of interest is some sort of yes/no kind of situation. Is this particular insurance claim fraudulent? Yes or no? But here are some more examples. From the realm of human resources, you can use logistic regression to analyze your data and say, hey, what factors are associated with high performers quitting? This is known as bad attrition. So you can take your HR data and build a logistic regression model where the outcome of interest is quitting, yes or no, and then analyze what factors might be potentially associated or predictive of that outcome of interest. If you happen to work in the nonprofit realm, what is the chance that a prospect or a lead will become a donor? Not surprisingly, nonprofits need donors to do their good work. So they're really, really interested in finding out what levers, what kinds of chance they have of actually converting somebody on a mailing list, for example, into an actual donor. Product management, use this all the time, both as when I was doing product management work, but also supporting product managers. Which features are highly predictive of a sticky customer? A lot of companies these days are trying to sell services, whether that's you get steaks delivered to your home once a month, that's a service, or software as a service, or whatever it might be. So product managers are super, super interested in understanding who's going to be sticky. That's a customer who pays month after month after month after month. So that's really super useful for product managers. Marketing, classic example. What factors predict paid conversion? In finance, this actually comes from my hands-on work. What is the chance of a particular credit card transaction becoming a chargeback? If you don't know what a chargeback is, that's when essentially you try to issue a charge on a credit card and then it gets disputed. And more often than not, what ends up happening is the credit card holder gets their money back and then you also get assessed a fee as the merchant. So it's really, really expensive. So finance people really care about this sort of thing. And that's just a small sample. Yes, no questions are everywhere in real world business analytics. Let's say you work in healthcare and somebody gets admitted to the ER. You could build a logistic regression model to try and analyze all of your ER patients to figure out what are the factors that drive them actually being admitted to the hospital, not discharged from the ER, but actually admitted to the hospital. Maybe that's super useful for you to know. There's many, many examples of yes, no. So logistic regression is wildly useful, wildly useful. Now, not surprisingly, in this crash course, if we're going to demonstrate what's going on with logistic regression, we need a data set. So I'm going to use the StatLog or HART data set from the University of California at Irvine or UCI machine learning repository. So you can certainly Google that if you'd like and go find it and get the original data set. But I'm actually going to provide you with the data that I'm using in this crash course if you use the link down below the video in the description. Okay, so this is the data set here. You can certainly look it up if you'd like. But at a high level, this is what the data is. This is like our data dictionary or our metadata. So what we have here are a bunch of features. That's machine learning terminology for a column, or if you're from a statistical background, a variable. But these are all columns. And these are the types of each column. Some are categorical, some are numeric, and here are descriptions of the various things that are going on. So for example, this data set has maleness defined as a categorical, where a value of 1 in a particular row for this particular column indicates a male patient, 0 otherwise. Now, getting even more specific using traditional statistical terminology with logistic regression, the outcome of interest in this particular data set, or the dependent variable, is heart disease, which is categorical. And it's essentially yes or 1 if heart disease is present and 0 if not. So this is a binary problem. This is a binary outcome of interest. So we can use binary logistic regression to build a model and try to analyze what's going on in the data. And then everything else are the predictors. All the rest of these columns, age, male, blood sugar, old peak, so on and so forth, are independent variables or the predictors. These are the things, these are the columns, these are the pieces of data that our model can learn how to predict the outcome of interest or the dependent variable. So we use this to figure out how to predict this, essentially. And then once we get a logistic regression model, and assuming that it's accurate in its predictions with the data, we can then interpret the model and then maybe derive some powerful new insights from the data. So that is our data set. Now, next up, we have to ask ourselves, okay, cool. Dave, you've used this term model. What is a model? let's get a little bit more concrete here, Dave. What is a model? So here is a working definition from Wikipedia, and I like it. Now, I'm not going to drain it. Feel free to pause the video and read the slide if you'd like. Let's talk about what's really going on here. So what's really going on here is that this crash course is all about abstract models based on this definition. And generally speaking, when you talk about machine learning and predictive analytics, that sort of thing, statistical learning, we're talking about abstract models, not physical models like model planes and ships. And logistic regression models are mathematical models. And usually when people hear that term mathematical model, in their mind's eye, they see something that looks like this, right? This kind of mathematical equation. Now, as we've discussed previously, logistic regression is all about modeling or analyzing binary outcomes. Yes, no, true, false, approve, deny, legit, or fraudulent. So this Y thing here has to be essentially yes or no, basically, at a high conceptual level. As we'll see later on, it's not exactly what happens, but right now, just think of it as coming back as yes or no, true or false, fraudulent, legitimate, approve, deny, that sort of thing. And all this rest of this stuff over here determines whether or not you get this or this. Now, with that background, let's just talk a little bit more about model equations. Now, and to do this, we're going to need a little bit of math here, but don't worry, don't freak out. It's not all of that complicated, okay? Now, the good news is that what we're going to learn here in this crash course is mostly conceptual. Python actually does all of the hard work behind the scenes for you. So another way to think about it is that Python does all the heavy lifting, but you still need to know enough to understand the quality of the model, and also more importantly, assuming that the model is of good quality, to interpret it. So that's what we're really going to be focusing on in this crash course. The kinds of things that you need to know to use these techniques effectively. And of course, if you want to learn more about the underlying math, I'll give you some resources later on. All right, I'm going to set the Wayback Machine to elementary school or middle school, and I'm going to ask, do you remember this? Y equals mx plus b. Not to sound like my dad, but back in the day, this is how I learned the equation for a line, or more specifically, the slope-intercept form of a line. Now, what's really interesting about this equation is it's quite simple. Imagine, if you will, some sort of chart. Maybe you're familiar with Excel or some other graphical tool like Tableau, Power BI, Python, whatever it might be. But think of a chart, right? You have an x-axis and a y-axis. And this line, this equation right here essentially describes lines that you might see on a chart like that. Specifically, the m represents the slope of the line. How steep is it going up? How steep is it going down? Is it flat? That sort of thing. That's what the m is. And the b here is where the line intercepts the y-axis on your chart. That's the slope-intercept form of a line. It's the mathematical equation for, any sort of line you might draw on a chart, on a 2D surface, x and y. Okay. Now, this is the same thing. Y equals b0 plus b1 x1. All I've done is kind of just move some stuff around and change the symbols a little bit, but conceptually it's exactly the same thing. So b0 becomes the y-intercept, b1 becomes the slope. And the reason why we do this is because we want to be able to scale beyond just lines in xy space, right? So for example, if I want to do a 3D line, I need an x and a y and a z axis. So the y equals mx plus b form doesn't really work that well, but these b0s allow us to scale. So we can take it up a notch. So we can say, all right, cool. I've got this new equation over here, and look at all these x's and ones, and let's talk about what these mean. So first up, y is our dependent variable. Right? This is the thing that we're trying to learn how to predict using logistic regression. In the case of our heart data set, y is heart disease, that column. Now, you might be thinking to yourself, all right, that's cool, but what about all these x's, Dave? x1, x2, x3, what are these? Well, these are our independent variables. These are our predictors. So these are things like male and blood pressure and age. Our predictors are independent variables. So if we have 3 columns of predictors, 3 columns of independent variables, we can use our notation to do this, but it also scales to 4, 5, 27, whatever it might be. Now, these B1s, B2s, and B3s are what are known as our coefficients. These are actually the numbers in our mathematical model, and we'll talk more about that later on. They're just called coefficients. That's all we need to know for right now. And then lastly, B0 is your y-intercept. Okay? So this is pretty standard stuff here, right? So if you're going to be using things like logistic regression, you need to make sure that you're comfortable with this. You don't have to be a mathematician by any means, but you got to be comfortable with the notation and understand these are coefficients, independent variables, all that sort of thing. And by the way, it's not really hard. You get used to it pretty quick, especially if you start writing some Python code, you get used to it fast. So let's use that information and really cement it using an example. So I'm going to use a hypothetical example. It might not be the best one in the world, but it's good enough. I've taught this many, many times and people seem to get the idea. So imagine you're a real estate agent. So you sell homes. That's how you make your living. You live in, let's say, Bozeman, Montana, where I live, and you make your money selling houses, helping people buy houses and sell houses. Okay. So you figure out that, hey, if I can build a predictive model for effectively pricing houses, that could help me out a lot as a real estate agent, because if I can pick the right price for my clients to sell their house at, they'll sell faster. I'll have happier clients. I'll get better Google reviews, and I'm just going to be very, very successful. So it's a good thing. Let's assume that. Okay. So in this scenario, the dependent variable, the thing that we're learning how to predict, is the price of a house. And let's say going forward that for this particular example, our independent variables are things like the size of the house in square feet. I live in the US, we use square feet. Many other places in the world use square meters, same concept. How much living space do you get? And we're going to call that X1. So this particular independent variable, this particular column in our data, this particular predictor of house in square feet is called X1. The number of bedrooms will be X2, and the number of bathrooms will be X3. Now, some of you that are watching this video might have some familiarity with mathematical modeling, maybe from linear regression or something like that. And you might be thinking to yourself, geez, Dave, all of these things are very closely related, or more technically, correlated. Yes, that's true. If you're thinking that, you're absolutely right. I apologize, but we're just trying to understand what's going on here. So let's not worry about that right now. And if none of that made sense to you, pretend like I didn't say it. All right, so we grab a bunch of data. So let's say that I'm a real estate agent, and in the United States, we have this thing called the Multiple Listing Service, MLS, and it provides data for all the houses that were bought and sold in a particular geography. So as a real estate agent, I can get that data. And let's say that I get that data and I feed it into my handy dandy modeling technique, and it comes up with a mathematical model that looks like this. Why? The price is dependent on the value of 135,000 plus all of this stuff over here. Now, we're going to get into what this means a little bit here in a second. But first up, I want to emphasize something that's really super important, because this hypothetical example illustrates a critical idea in predictive analytics, no matter what technique you're using. The models, the predictive models that you create, are based only on the data you provide, the machine learning technique, the machine learning algorithm. So in the case of this particular model, these values here were estimated from the data. As the real estate agent, if I can get more and better quality data, these estimates or my model will tend to be better. Garbage in, garbage out applies, right? If your data is terrible, it doesn't really matter. But if you have good data, high quality data, the more of it you get, in general, the better the model is. But the model is always constrained by the data that you have. It's only as good as its inputs. So that's really super important. So if you decide to do logistic regression analysis and then report your findings to your stakeholders, you need to properly set their expectations that this model is not perfect. In fact, it's going to be wrong a lot of the time. But is it actually useful? That's the main thing. And the usefulness will be based on the data that you feed it. Okay, so enough of the soapbox. All right, so let's assume that this is our model right here. And let's say we have a new client. A new client comes in and they say, hey, Dave, I want you to sell my house for me in beautiful Bozeman, Montana. And here are my stats. My house is 2,300 square feet. It's got 4 bedrooms and it's got 2.5 baths. Nothing fancy, pretty standard suburban house here in the United States. So all we do is we plug and chug. We say, okay, 2,300 square feet is X1. X1 is right here. You see that? X1 right here. So boop. 4 bedrooms is X2, goes right here. 2.5 bathrooms goes right here, because that's where X3 goes. Okay, we say, all right, cool. And all we do is we plug and chug. So we just multiply this together, goes here, multiply this together, goes here, multiply this together, goes here, and then we get a final result of $211,645.19. So based on our model, this is what we should list the house at. You might be thinking to yourself, hey, wait a second, Dave. That's not a yes, no. That's not a yes, no, Dave. 211,000 is not yes or no. How's this going to work with logistic regression? And for that, we need another tasty tidbit of math known as the logistic curve. The equations that we've seen from the previous slides, those mathematical models that we've seen, the slope-intercept form of a line, as well as our housing pricing model, the hypothetical model, these are equations, these are mathematical models that produce straight lines. So to give you another really contrived example, think of the equation for relating degrees Celsius to Fahrenheit. So if I have degrees Celsius along the x-axis here, and I have Fahrenheit along the y-axis, there is actually a mathematical model, a linear model, a equation that does this. So you take 1.8 times degrees Celsius, and then add 32, and that gives you degrees Fahrenheit. And there is a strict linear relationship between these two things, right? You can perfectly predict, if you will, degrees Fahrenheit from degrees Celsius using this mathematical model. But notice that it's a straight line. However, what we want to do is we want to predict binary outcomes. We don't want to predict straight lines. We don't want to predict even wavy lines, right? Or circles or whatever shape you can think of. We want to predict yes and no. That's what we want. So what we need is the ability to transform something like this that would normally give us a straight line or any other sort of shape and actually translate it into something that we can interpret as yes or no. And that's what the logistic curve does. What the logistic curve does is take the output of these kinds of models, these kinds of equations, and then transforms it into this nice little smooth curve that ranges from 0 to 1. And this is what logistic regression does. It combines these two things together. Now, one thing you need to note is that this particular logistic curve here will never actually reach 1. It'll get very, very close, like 0.99999, but it'll never get to 1, and it'll never get to 0. It might get to 0.00001, but never actually get to 0. So in strict terms, these are known as asymptotic. So they get really, really close, but never there. So this is super useful. So we just basically interpret this as a value between 0 and 1, even though technically it never gets to 0 or 1. It gets really, really close. So let's put it all together. We've got our situation where we know that our logistic regression models are going to look like this, right? They're going to be some sort of mathematical equation, right? Here's our intercept and our various coefficients and our various independent variables, so on and so forth. But we need to convert these into labels. Yes or no, approve, deny, true or false. These are known as labels, right? They're categorical outcomes. So what we do is we use this little piece of math right here. We use 1 over 1 plus e to the negative x. Okay, I'm going to ignore the negative x here for a second and just talk about this thing e. This is known as Euler's number, and it's around 2.7-ish. And Euler's numbers are a really important thing, well beyond the scope of this particular crash course because of the mathematics, but that's just what it is. So we're going to take Euler's number, about 2.7-ish, and we're going to raise it to a negative power. And if you don't remember, when you raise something to a negative power, this actually becomes a fraction itself, essentially. Let's not get bogged down in the math, as I promised. Let's talk about the intuition. So the logistic curve gives us the probability, the percentage chance of a label occurring in the data. Right? Because remember that logistic curve is that kind of S shape and it goes from 0 to 1. So we interpret it as a probability or a percentage chance. So for example, traditionally, if anything is greater than 0.5, we typically say, yep, the chance of it happening is positive. So for example, is this particular credit card authorization fraudulent? Yes or no? And if we look at the logistic curve and if the logistic curve said 0.55, we would say, yeah, it's probably fraudulent. That's an example of how you interpret this, okay? So don't get bogged down by probability. If you don't like that word, think of percentage chance of something happening, okay? And if it's greater than 50% chance, we typically say, it's a safe bet that it's going to happen. Now, when we combine these two things, that's where we get the magic of logistic regression. So what we do, essentially, is we take this and we put it in right here. And that's a bit abstract, so let me show you what I mean. Okay, so this is typically what a logistic regression model looks like from a purely mathematical perspective. What we do is we just take this thing here and insert it right here. So what we do is we put our linear model, our linear equation, thing that gives us straight lines, and we just put it right here, and voila. What we get out now is the probability of something happening. That's what this P means, probability of Y, which you can just think of as a percentage chance from 0 ranging to 1. Now, with these ideas, let's talk about your first model, your first logistic regression model. We're going to talk about it in slideware. Of course, you will also get the code if you decide to get the files from me down below in the video description. All right, so we're going to use the hard data set. And what we're going to do is create a logistic regression model that's extremely simple. We're just going to say, look, we're going to use one feature. That's it. Can we use one feature to predict heart disease? And we're going to use maleness. Maleness is going to be our X1. And from our metadata, we know it's 1 or 0. So if the patient was designated male, they have 1, otherwise it was 0. And here is our equation, right? So we have one feature, one independent variable, and we'll have a coefficient corresponding to that. And then here is our y-intercept. We always have a y-intercept. You don't have to, but by default you get one, and you very rarely never want to have one. So that's why I said you'll always have one, even though technically it's not 100% correct. Okay, moving on. So you put your heart data set into logistic regression. You say, hey, find me a model to try and predict heart disease from maleness. And the computer chugs away, Python chugs away and says, yep, I can do that for you. And here are the estimates. So B0, or your slope, your y-intercept is negative 1.2090. And maleness has a coefficient value, B1, of 1.3953. So all we need to do is plug and chug, right? We just plug it into the equation that we saw before. So we got our B0 here and our B1 times our X1 right here. And if you're male, given this logistic regression model, what's the probability? What's the percentage chance you have heart disease? So we just run the math through, just keep running the math, and then what we get here is 0.5469. So based on this simple model of just taking the rows of data, and there are 270 rows of data in the hard data set, so it's not a lot of data. So the model is limited by the amount of data that we have. The data is high quality, but it's limited because there's only 270 rows. But given the limitations of the data set, we would predict just based on maleness alone that 54.69% of the time, per the data set, you have heart disease. Now you may be asking yourself, geez, Dave, is this a good model? And the answer is, maybe it is, maybe it isn't. So what we need to do is figure out what is a way for us to say, look, no matter how we construct our models, whether we use one independent variable, one feature, or we use 5 or 12 or whatever it might be, we still need to answer this question, is it a good model? And for that, we need some sort of reference. We need some sort of baseline to compare it to. So let's talk about that. So first up, we've got our first model. So to establish a baseline, what we need to do is think about our data set. Because we have our model now, right? That male model. Right? That's what I'm going to call it, the male model. X1 of maleness as being the only feature in the model. And we need to compare it to our overall data set and say, okay, what would the baseline be? So the data has 270 rows, also known as observations. And of the 270 observations, 120 have heart disease indicated, or label of 1. They have a label of 1, so 120 out of 270. So what we do is we say, look, all things being equal, if you had no logistic regression modeling technique, if you had nothing else, all you had was just a bunch of rows of data. In general, what you could say is, I could estimate the chances of you having heart disease just based simply on the proportion. And the proportion in this particular case is 120 divided by set 270, right? Because out of the entire data set, only 120 folks out of 270 have heart disease, and that's about 44%. 44.44%. So this is the baseline model that we use. This is the simplest predictive model. If we have just a yes-no kind of situation, we just predict the proportion of labels. That's the baseline. So what we want to do is we want to beat this because we can say, look, using only the labeled data, we would predict heart disease 44.44% of the time, which basically we would say is nobody has heart disease using that 50% cutoff. And that's not great. So what we want to do is create models that are more useful than this. Okay, we want our logistic regression models to beat the baseline. Now, the good news is that almost always it beats the baseline, just so you know. It's actually ridiculously easy most of the time to beat the baseline. But we still need to cover this because you're going to see it in the Python output. Okay, you're going to see the baseline score. So what you do is you think about the baseline as being a comparative tool, because usually what you're doing in a logistic regression analysis is you're making multiple models. You might start with a male model, for example, and you might be like, that's not very good. So I'm going to add age and blood pressure and angina and some other features. And as you add more features, in general, you would hope that your model gets better. It improves. It beats the baseline by more and more and more. Now, there comes a point where you might add in too many features. You might add in features that aren't particularly useful. So not only are you going to compare every one of your models to the baseline, you will also find out later on how you can compare your first iteration of a model, not only to the baseline, but the first iteration of your model to a second iteration. And then you might be like, well, the second iteration is better than the first. So you go, okay, cool. Second, then you do a third iteration and you say, oh, wait a second, the third iteration is not as good as the second iteration because maybe I added a feature that isn't very powerful to the model and it reduces its effectiveness. So you're going to learn about all that. But first, we're going to talk about the baseline. What we're going to do here is start talking about our baseline model. So our baseline model essentially predicts no heart disease using that 50% cutoff, right? It predicts only 44.44% of the time. Does anybody have heart disease? So in general, we think, okay, that's not too risky. But then we can look here at the male model. The male model has a value of 1 when the patient is male and 0 otherwise, and we can calculate the probabilities for each one of these situations. What's your probability if you're male, right? So the probability of Y being male, that's what this means, right? You are indicated as male. And we saw that already at 54.69%. And then otherwise, you're not set up as male, is 0.2299. So given this, the model only predicts that males have heart disease. However, if we think about it, that's actually an improvement over this over here, because the baseline model says, well, all things being equal, predict nobody has heart disease because the probability is not more than 50%. What we want to do, though, is we don't want to rely on human beings to interpret this stuff, right? Hopefully you agree with me that's not a good idea. So what we would like is a standardized way for us to understand, is one logistic regression model better than another, and not rely on human subjectivity. And that's where this idea of goodness of fit comes into play. Like I said, we don't want to leave this to gut feel. So not surprisingly, statisticians feel the same way. So they figured out a mathematical, standardized way to compare logistic regression models. And this is typically known as the goodness of fit. And the goodness of fit calculation that we're going to be studying in this particular crash course is known as the log likelihood. But before we look at the math, let's think about why the math is the way it is. Let's think about it at an intuitive level. What would we want? What characteristics would we want from our goodness of fit calculation? So, easy way to think about this is, in the event that our data has a label of 0, so let's say, for example, a row of data, one of the 270 rows of data in the heart data set has 0 for heart disease. That's the case. We want our model to actually fit well when it predicts a probability close to 0. So if our model is very, very good at predicting when people do not have heart disease, for example, we want the goodness of fit calculation to reflect that. We want the math to say, oh yeah, Dave's model is pretty good at this particular scenario, that is, people that do not have heart disease. So in that regard, it's a good model. So the score should reflect that. Hopefully that makes sense. Reflexively, when a label in the data is 1, so in the case of the heart data set, somebody actually does have heart disease, the model fits well when it predicts a probability close to 1. And we want the math to also reflect this. So our models are good when it predicts close to 0, when in fact the label is 0, and good models predict close to 1, when in fact the data is 1. And what we want is math to actually to embody this idea in a standardized way. So here is the log likelihood calculation. Okay, so don't freak out. We're not going to really go through it in any sort of level of detail. These LNs here are known as natural logarithms. I'm not going to talk about natural logarithms in this particular crash course. You're welcome. We're just going to focus on the intuition. Okay. So this E thing, this squiggly E looking thing is known as a sigma, if you're not familiar. And the way to think about this, if you're not familiar with sigma notation, is this just says go through all the data and add it all up. So there's 270 rows of data. Start with row 1, go all the way up to 270. So for every row of data, go through everything and add it up. And what it's adding up is everything to the right here. So for row 1, it's going to calculate this thing. For row 2, it's going to calculate this thing. Add those together. For row 3, it's going to calculate this thing. Add row 3 into the previous total and just keep going through. Okay. If you're familiar with coding, this is like a for loop, right? It just runs through a whole bunch of calculations. That's the intuition there. Now, these little y sub i's, these are our actual label values in the data. So these are our zeros and ones. In the case of the heart data set, did you have heart disease? Yes or no? 0 and 1. Now, this P of yi is actually the model's prediction for a particular row. And we're going to see this in more detail on the next slide. So what we do is we're just going to go through every line, every row of data, and just run the data through this particular calculation. We're going to grab the actual labels, 0 and 1 from the data, and then we're going to grab the model's prediction for each row of data and then run it through this equation. And I'm going to do the math for you so you don't have to worry about it. Because once again, we're going to focus on the intuition. Here's our log likelihood function right here. And let's imagine, if you will, that we only have 4 rows of data. Just trying to keep it simple. So we have 4 rows of data, row 1, 2, 3, and 4. So you can see here our i's are 1, 2, and 3, and 4. Now, in Python, of course, Python starts counting from 0, but just to make things easy, I'm going to start counting from 1 instead of 0. All right. And what we can see here are the individual labels. So some of these are 0 labels, and some of these are 1 labels. And what we can see here is the model's prediction. Okay, so we have our label and our model's prediction. And notice what's going on here. Notice that for this particular row of data, row 1, the actual label value is 0, and the model's prediction is very close to 0. So this is good. The label is actually 0, and the model predicts something very close to 0. That's goodness. Ooh, unfortunately, this row 2, not so much. The actual label in the data is 0, nothing's happening, but our model's like, no, I think something's actually happening, which is not good. Over here on row 3, we can say, hey, I've got a label of 1, something actually is happening in the data, but the model's predicting that nothing's happening. And then lastly, yep, something's happening, and the model predicts, yep, something's happening. So out of these 4 rows of data, we can think of 2 of the predictions as being correct. Row 1 and row 4. Row 2 and row 3 are incorrect. Just keep that in the back of your mind, okay? Because we want to build the intuition. So moving on, I'm just taking various pieces of this equation here and just running the calculations for you. And this is okay. We don't need to drain it. You can pause the video and look at it if you would like. But once again, we're going to focus on the intuitions here. So moving on, just doing other pieces of the calculation here. And what we want to do, though, is actually look at the row totals. This is what's super important. Because remember, rows 1 and 4 were correct. And rows 2 and 3 were incorrect. And look what happens way over here in the row total. That's immensely interesting, right? Notice that these row totals are exactly the same. Notice that those things that are correct are very, very close to 0 in terms of their magnitude, and those that are incorrect are very, very far away, relatively speaking, from 0. And notice they're exactly the same. So this is the magic of the log likelihood, right? It's encapsulating this idea mathematically that when my predictions are quote unquote correct, that I'm going to get a very, very low row total. I'm going to get a low magnitude row total. When my predictions are incorrect, I'm going to get a much larger result. And that's what we want. We want a standardized math calculation that encompasses this idea of saying, look, when I want to evaluate a model, I want to score it well when it does well, and I want to score it badly when it does badly. So here are some things that we need to remember based on what we see here. The log likelihood, because of the math, is always negative. Notice how we always have a negative sign here. That's okay. It doesn't really matter conceptually to us that it's negative. Log likelihood, the calculation, scores correct predictions close to 0. Now, these are negative values, but the closer to 0, or the closer, I should say, to being correct, that's a better way of putting it, closer the predictions are to being correct. For example, this is really close to being correct, and this is really close to being correct. the closer to 0 it is. Now, you might have a situation, for example, here where the actual label is 1, and maybe your model predicts 0.8 instead of 0.9999. That's still technically correct, but not as correct as 0.999. So what you will get is a score that's a little further away from 0 than what you see here. That's the intuition. And then next up, we know that incorrect predictions are far away from 0. So in general, the most useful, and if you want to think of it this way, the most accurate logistic regression model, binary logistic regression models, have grand totals, when you add up all of these row totals, close to 0. So for example, I have 270 rows of data in the hard data set. I would have 270 row totals. And then all I do is I just add up all those 270 row totals, and that gives me the grand score for my goodness of fit, or my grand log likelihood. A model is better if it's closer to 0 in terms of its log likelihood score than another model, which is nice because now we've standardized things. And the good news is Python will calculate this all for you, and all you do is just compare the numbers, which is nice. Let's start talking about how we do logistic regression with Python. So what we're going to do here is load up our hard data set. And we're just going to do nothing fancy here. We're going to import pandas. We're going to use read CSV and read the CSV file. Again, I will send you the CSV file using the link down below. And you can see here I'm doing a head here on the hard data frame, and you can just see the first 5 rows and all the various features. And the first model we've already seen. It's the male model. We saw it in slideware earlier, but now we're actually going to do it in Python code. We're going to try and predict heart disease using maleness as designated here in this particular feature. So here's how we do it. We're going to use a library in Python called statsmodels. Now, if you're familiar with machine learning in Python, there's another very popular library called scikit-learn. Scikit-learn also has binary logistic regression models in it. However, that particular library really is not set up for data analysis. It's really set up for purely just like building predictive models and hooking them up to your website, things like that. If you want to do really good, heavy-duty logistic regression analysis, you want to use stats models. It's really designed for that. So that's why I'm using the stats models in this crash course. Okay, cool. So what we're going to do here is use a particular library here from stats models that allows us to use text to declare what our models look like. And this is what's known as the formula API. And it's really super useful. So I'm just going to import the stats models formula API as SMF, excuse me. Stats models formulas. That's what I'm using SMF for. And within SMF, logit is the function that we want to use for creating logistic regression models. And the reason why it's called logit and logistic regression is a mathematical thing, well beyond the scope of this crash course. Just know that logit is what you want to use, okay? And we say, hey, okay, logit, here's my formula. And my formula is my way of using text to declare the structure of my logistic regression model. And you can see here, heart disease, tilde, it's a little squiggly here, on a US keyboard. This is usually by the 1 on your keyboard, and male. And the way to think about this is, hey, stats models, build me a logistic regression model that will predict heart disease by male. Heart disease by male. And stats model says, cool, I can do that. Give me some data. So I'm going to pass in my hard data frame here. And this is a column, and this is a column in my hard data frame, and everything works. By the way, as an aside, one thing to remember is logistic regression analyses like this don't work when there's missing data. So every row and every column has to be completely filled out. Just keep that in the back of your mind, okay? So that is the case with our hard data set, so everything works just fine. And we get back an object here, which we're calling heart_model_1. Not a great name, but just go with it. I should have probably called this the male model. And then what we can do here is then call fit. Fit essentially is a naming convention in stats models that comes from scikit-learn as well. And this is a very common nomenclature that says, look, go learn from the data. Okay, you've got your model defined, you've got your data, now go learn the model, go learn from the data. And then when we get back from there is another type of object, which is known as our results object. So a model_1 results, and I can then ask to print out a summary of my model. So I just call results, call summary on it, and then I'm just going to print it out. And this is what you'll see, for example, in a Jupyter notebook in your output. There's a bunch of stuff here. We're going to go through The most important pieces, we're not going to go through everything. There's no way. This is a crash course. We can't go through all the output here. We're just going to go through the stuff that matters the most. So first up, LL null. This is basically the baseline model. And notice the score for the baseline model here is negative 185.48. So this is the way to think about it is you can even just ignore the negative if you want. Just say, look, this is 185.5 tick marks away from zero. Is that a good model? Is it a bad model? You don't really know. You have to compare it to something else to understand. So this right here, the log likelihood score, this output is your current model. This is the male model. And what you can see here is that the male model is about 173 tick marks away from zero, but this is 185.5 tick marks away from zero. Since this is closer to zero, this model is better than the baseline, but not by a lot. Hopefully you can see that, right? It's only about 13-ish tick marks closer to zero than the baseline model. So yes, it's an improvement, but not by a lot. So this is your first model. We've just kind of cemented a whole bunch of ideas into actual Python code, into actual results here. Now, what we need to know is that most of the time, simple's not going to cut it. Okay, a simple model with only one feature, with one independent variable, usually is not that useful. So what we need to do is we need to add complexity. Simple logistic regression is what we saw in the last model, where I have a single independent variable, a single predictor. That's a simple model. What we're going to learn about here now is multiple logistic regression, where we can actually use more than one feature simultaneously, more than one independent variable. So we already know how we can do that. We just add more X's and B's here. And we can try and improve upon this male model by adding a second independent variable. So maybe we'll say, look, maleness is not good enough. Let's also put age in there, because we think age is probably highly associated, highly predictive of heart disease, which, I mean, we all know what it is. So here we go. So we're going to go ahead and add in age here, and that's going to become our X2, B2. And all I'm doing here is just showing you just a subset of the actual heart data set. Okay, so we got heart disease, age, and male. So heart disease is our Y, this is our B1, and this is our B2. Excuse me, this is our X1, and our X2. The B1 and B2s are our coefficients. We just go ahead and we just run everything through, right? Nothing changes. Everything that we've learned so far does not change, whether we're using one feature, two features, doesn't matter. You can have any number of features. This is the great thing about the way logistic regression is set up. Once you learn the basics for a single feature, a single independent variable, conceptually, it just scales to whatever else you want to do. So let's see how we can do this in code. Not surprisingly, all we do is just add in age. Okay, so everything is pretty much the same, right? You could literally have copy and pasted the code that you saw earlier into a new cell, like in a Jupyter notebook, and just tweaked it a little bit. So we can say heart disease by male and age. That's what the plus symbol is, not surprisingly. Male and age. And we're going to call this heart model 2. Could have called this the male age model. That's probably a better name. We're going to fit it like we saw before. We're going to get our results back, and then we're going to print the summary so we get a nice output in our Jupyter notebook, let's say. And here we go. So notice that the baseline model is still negative 185.48. That's never going to change because the proportion of labels is always the same. And now what we have up here is our new log likelihood for our second model, which has both maleness and age. And notice that it is 164-ish tick marks away from zero, which is better than 185. And is also better, by the way, than the first model. So the second model is an improvement over the first. And that's why these log likelihoods are so important, right? Watching these scores. Because as you hypothesize about what features should be in your logistic regression models, you can run them real quick, check the log likelihood scores, compare one model iteration versus another, see what's going on, keep iterating until eventually you reach a model that's optimal for you and useful for your business. Once we have a model, we still need to be able to interpret the model results because generally speaking, let me go back up a slide, you don't want to show this to your business stakeholders. Unless they happen to be statisticians or actuaries or something like that, they're not going to be happy with you if you show them this. So what you need to do is interpret the models for them. So what we're going to do is we're going to create a third model and we're going to add angina. And if you're not familiar, angina is a heart condition. And this is a binary indicator, 1 or 0. Okay, so we're going to say, look, we're going to try and predict heart disease by the combination of maleness, age, and whether or not somebody has angina. And all this code, basically the same, boilerplate. Right? I've just switched up the name to heart model 3, changed this model specification here, model formula, and I can go ahead and run the summary, and boom. What we can see here is our baseline is the same, And we've improved yet again. Not surprisingly, right? So as we've added features, we're getting closer and closer to 0, which means our model tends to be more and more accurate based on the log likelihood calculation. Okay, so we want to try and get as close to 0 as we possibly can. All right, now, how do we interpret things? Well, the first thing that we're going to want to look at are these things known as confidence intervals, and these are right here. This is the first thing that we're going to want to look at, and here's why. You can think of confidence intervals as representing the range of plausible values for your model coefficients. So for example, the 95% confidence interval for maleness is between 0.813 and 2.117. So let me go back up a slide. So maleness right here is our first feature, 0.813 to 2.117. So that's a plausible value. And what we're looking for in particular when we look at this is 0 not included? Or reflexively, is 0 included in the range? And notice that 0 is not included in this range. 0 is not included in these ranges. And what that means is when 0 is not included in the the confidence interval, it means that the coefficient is statistically significant. And that's just a fancy way of saying that the predictor is important. Because if the coefficient is 0, it includes 0 in the confidence interval. What it's telling you is, maybe sometimes this predictor is useful, maybe sometimes it's not. But if 0 is never included in the confidence interval range, then you know that the predictor is super important. And this is a key idea. So the first thing we want to look at. And of course, if you want to learn more about confidence intervals, I'll give you some resources later for that. But conceptually, this is what we're looking for. Are our predictors important? And as long as 0 is not included in the confidence interval, we know that they are in fact important. Now, interpretation is also useful as well, because if you want to get fancy, you can also provide these ranges. You can talk about these ranges of values to your stakeholders. I typically don't do that very often, and I'll explain to you why here in a few slides, but you could if you wanted to. Now, one last thing I should mention is that these confidence intervals are estimated from a data set and for a particular set of independent variables. So if we added a fourth feature to this model, So let's say we added blood pressure. These would change. These confidence intervals would likely change for male and for age and for angina. Just so you know, these are calculated per a set of independent variables. If you keep your data set fixed, which you usually do as you iterate, you're going to see these things change as you try out different features. Just keep that in the back of your mind. Let's talk about the coefficients. Here's our coefficients here. We've already looked at these confidence intervals, and we know, all of our predictors are important because none of these confidence interval ranges include 0. So these are all statistically significant or important. So let's talk about what the coefficients actually mean. What we're going to need is another little piece of math, unfortunately, or fortunately, depending on how you look at it, to interpret the coefficients. And the math that we're needing is odds ratios. Now, the good news is that odds ratios are pretty easy to understand at an intuitive level. But what we want to understand is the mathematical relationship between our coefficients and odds ratios. And here it is. So an odds ratio can be calculated by taking Euler's number. There's that E thing again, Euler's number, 2.7-ish, raised to the power of one of our coefficients. So let's really cement this with an example from our third model. The male independent variable had an estimated coefficient of 1.4648. If I plug that in to this thing here and take Euler's number and raise it to that power, I get back a value of 4.3265. Okay. Now, in Python code, this is how you would do it. You can say, hey, from math, import exp. That stands for exponentiate. That's what this is, exponentiation. And I just do this, grab the male parameter, the male coefficient, exponentiate it, and then print it out. And you can see here, I get the exact same value. Given that background, let's start talking about what we can do. So what we're going to do here is we're just going to exponentiate each of our coefficients. And we get this one. And here's how you interpret it in natural language that your stakeholders can understand. The model estimates, remember, we want to use that word estimates, okay? We want to make sure we're properly setting expectations here. The model estimates that males are about 4.33 times more likely to have heart disease than those that are not designated as male. Now that is right there, that illustrates some of the power of logistic regression, because most business stakeholders, in my experience, can understand something like this. Oh, so if they're male, they're 4.3 times more likely. Okay, super interesting. Moving on, we can exponentiate age. Now, age is a little bit more complicated because notice that male is like this, and age is just basically a number, not to be cliche. Age is just a number. But in this particular case, this is the result we get. When we exponentiate the coefficient for the age independent variable, we get back 1.0633. Now, this is how you interpret that in natural language. The model estimates that each year of age raises the relative risk of heart disease by 6.3%. Now, here's the way to think about it. So if I'm aged 40 and then I go to age 41, that means that I am now 6.3% more likely to get heart disease than when I was 40. But it doesn't mean I go from like 40% to 46.3%, right? Because maybe my percentage chance at age 40 was maybe 25%. So it's only 6.3% more than the 25%. That's the way to think about it, okay? It's a little bit more complicated, but it's also relatively interpretable. And then lastly, we have angina, and this one's a whopper. Right, look at this. The model estimates that patients with angina are 6 times more likely to have heart disease. So this is really at the heart of logistic regression analysis, is this idea that we can mine our data for interesting associations, predictive relationships. We can then interpret the models for our business stakeholders using odds ratios. And of course, we can also check all the things to make sure that our models are actually improving and that our predictors are actually important or statistically significant. Okay, so if you're excited to learn more, here is how you can continue your learning. So here are 2 great books. So this book right here is free. You can Google it, Introduction to Statistical Learning with Applications in Python. There is some coverage of logistic regression in this particular book. This book is really, really good, but it covers many, many types of statistical or machine learning techniques. So the coverage for any particular topic is actually relatively low. It's not in depth. This book over here is the single best, most accessible resource I have found for logistic regression by far. Discovering Statistics Using R. So this is written primarily by Dr. Andy Field. He's a psychology professor. So this book was written by a psychology professor for psychology students. So it is really designed for a broad audience, right? Because obviously most psychology students don't take linear algebra and statistics and multivariate calculus and things like that. So this is a great book for anybody that wants to learn more about logistic regression. Now, here's the thing. In the old days, the fact that this book was using R code would be a problem, but in the age of ChatGPT, not a problem. You can still learn all the concepts in this book, and if needed, all you do is just ask ChatGPT to translate the R code into Python, and you're off and running. So this is a great, great book as well. You can get this from Amazon. It is a big textbook. It's like this thick, so it covers lots of other things as well. So if you're interested in learning more statistical techniques, can't recommend this book enough. There you have it. I hope you enjoyed this particular crash course on logistic regression. Hope you like those resources. I'll put links to those resources down below in the description. Also, if you tend to like an online course over self-study, be sure to check out below where I list some of my machine learning courses, and you can get a 20% discount on those machine learning courses. All right, next up in this series, I'm going to do a crash course on text mining using Python, and in particular, the Mighty Natural Language Toolkit, or the NLTK. And when that's ready, it'll show up here as a tile on the screen. You can just click it. And in the meantime, I'll put in another one of my data science machine learning videos, just in case you'd be interested in watching that. All right, until next time, please stay healthy, and I wish you happy data sleuthing.